Back. So we're going to start the next session that is revolving around GPUs. It's a two-parter. So the first part is going to be from CSCS, and the second part on GPUs is going to be from Creative. So looks like we're kind of back on schedule in terms of time, which unfortunately for Erez means less time for him to finish his presentation, but that's okay. So with no further ado, let me hand it off to Sadaf.
Thank you. Can everyone hear me? All the way back. Thanks. All right, so I'm giving this talk on behalf of my colleagues, just because my surname starts with A, nothing special. I think everyone did more work than I did, probably. So during the last session, Gilad mentioned quite a few things about GPU and top 500 and all the rest. And he mentioned one thing about having very low efficiency for GPU-based clusters. So we cannot resolve all those issues through InfiniBand cluster connection, because some things have to do just getting DGEM efficiencies out of the GPU devices that are needed for LinBack. But I'm going to introduce this idea that has been around, and I think everyone is talking about it, but give you more bit like a deep dive. What exactly this GPUDirect is, how it works, and what you can expect, more importantly, in terms of your application. Work?
Page down.
Page down. Oh. Okay. Oh, that's the last page. I'm done. Yeah. Thank you. Okay, so how do I use it? Yeah, it's okay. And I guess I probably don't need to convince you why we are looking at GPUs, because we are getting a lot of floating point computational performance out of these things. And as it was mentioned earlier, 2 of the top 3 systems have these devices as the main compute units. So what we are here looking at, what is the difference when you do MPI or I/O from GPU versus CPU? So if we look from a traditional CPU point of view, so you have 2 types of devices, both connected through your PCIe chipset. And these are typically what we have in our systems, but I think the way you would connect it is not going to be substantially different. And when we look at traditionally, CPU is workhorse for HPC floating point operations. And prior to this emergence of Tesla-based GPUs, based HPC system, GPU was simply not in the picture. So when we look at traditionally what is going on, GPU has some memory attached to it, and then host has its host memory attached to it. And when host sends down some work to GPU for some acceleration, there is some exclusive memory copying that goes on between host memory and GPU memory. And if unfortunately that data needs to get out to the network for MPI communication or for I/O, then this data not only needs to be copied back to the host memory, but traditionally there used to be an internal additional copying going on within the host memory from one device to another device address space. So as you could see, that you could imagine a scenario where you are computing something in GPU and you have to send it directly to the network, because as GPU become main workhorse, you may want to do it more often. Then there is a lot of overhead there. So what GPUDirect did, it was just not necessarily a fundamentally different thing, but say, okay, without any due changes in hardware or essentially in system software, what we can minimize, which overheads can easily be minimized there. So this whole idea of GPUDirect came about. So this is, and I would emphasize, this is only just the first step. So essentially, everything remains the same. The only thing we do is use this pinned memory region in the memory, and this additional copying within the host memory is removed. So as earlier, there was a copying. There is a copying that is going on explicitly between host memory to GPU memory and GPU memory back to host memory. But what happens is when that same data needs to be transferred over the network, you eliminate an additional copying. And there are some requirements in terms of you have to allocate it PIM memory, and potentially, if you just look at it, you may be able to reduce some overhead, and that's something we are really looking at in this study. So, just giving you a little bit of motivation and introduction, what I'm going to talk a bit later about how do you set it up. I mean, there is documentation around, you can follow it, and that's pretty much what we did with a little bit of deviation. And then I will show with very simple examples, not necessarily any application-based examples that you really find online, is how do you observe it? How do you see what is going on? What activity is happening? I mean, there is no blinking light that tells you, okay, GPUDirect is happening. And there we used Ohio State, CUDA, and OpenCL examples. So if someone tells you, okay, you can't see that activity using in OpenCL, that's not quite true. And then I'll talk a little bit about how we tried to experiment with this thing, with GPUDirect on full-scale applications, and we were, for the most part, not quite successful. And this is the way things are now. And if not just us first, but some other centers tried to build systems with more GPUs, what we should do differently, or which technologies we should invest and investigate. That's something I'm going to say. So this is in some way prerequisites. I mean, of course, you can pick up any x86 platform, but what we really need is a Fermi generation Tesla card. It's not going to work on any GTX card, and then you need some HCAs and all the essential bits. In terms of software, again, then you have certain limitations, or you need certain versions of software environment. And you don't need to copy anything. There is a very nice white paper been done quite some time ago that gives you like a step-by-step. Some of those I would show here, but you can just download that and start copying those steps if you have a hardware lying around, which you can afford to tweak. Because I was told that after you set all this thing up, the system is not in a very stable condition often. So you install the kernel, you install the driver, all the necessary steps. In this case, Chris luckily did all this for us, so I don't know if any of this was a major issue. And all these steps you can follow in terms of NVIDIA driver and SDK installation. And except, as I was told by Chris, that except for one step, everything worked pretty much as it was listed in the white paper. So one of the things, once we set it up and we started experimenting with some code, the question that came about was, how do I know it's going on? I mean, because you see, in an ideal situation, the difference is only 30%. And in terms of semantics of anything you are running on, you really don't see a difference, because exactly the same set of thing is going to happen with a little bit extra efficiency. So then we found out, and it's also listed in the white paper, that you have to observe certain set of parameters, first for enabling and disabling GPUs, and the values that should change after the activity. So these are, I will show a little bit more example later on. And then, so you can simply open up another shell and start monitoring these values just by launching this script. And as you run your application, after it's complete, and if a GPU activity did happen, you see those values being changed. Then the other thing is, especially when we were doing the experiments, we said, okay, how do you enable or disable this GPUDirect activity, so we can see that there is a benefit enabling it and there is no benefit enabling, just for benchmarking purposes. So there are different ways to enable or just disable GPU. In method 1, of course, you can use environment variable, but as you would see, it changes your protocol. And in method 2, you have to be a root, and as one of the parameter we showed earlier, you can change it and then ensure if it's disabled or not. So when you get MVAPIC, you get these, or you can even get these benchmarks separately. So in this case, we used a modified version of Ohio State bandwidth benchmark, point to point. And this was written by Ohio State, and these are the, if you just look at go in the code, there are, I think, 1 or 2 places there are if-defs, I think 3 places just to do CUDA free. And essentially, what you see here is pinned memory allocation for sends and receive buffers. The way this benchmark is written right now, we are not really sending anything down to the GPU for any computation, but essentially what we are saying is we are going to use the pinned memory region for GPU and for MPI communication. So it's really as simple as that if you are using CUDA. So the equivalent version of the code, which we modified and wrote in OpenCL, and as some of you probably know already, OpenCL is a bit verbose. So not a whole lot of things are happening here, and most of this could be easily redundant. So once people start writing OpenCL code, sometimes they just go in and write wrappers around it. So it may look very scary just to do the same thing as it was done here, but once you get a hang of it, it's really not that much of a problem. So essentially, you set up your platform, because then you create a context, and after that, and again, this is something, it's not as straightforward, although as of in case of CUDA, but when you search quite a bit, you can identify and find out how to use pinned memory in OpenCL. So then once you create the buffer, and then you have to enqueue and map buffer. So these 2 statements together make sure that you are using pinned region. And if you know, in case of NVIDIA devices, the OpenCL driver is provided by NVIDIA. So then everything works pretty much the same. I don't know for sure, maybe underneath the share, probably the runtime shares a lot of similar code. At least it seems like to us, we can't check. So Hussein was the person responsible for setting up this platform. Nothing, again, special here. I think the only thing that I would highlight is just these InfiniBand. We have a little switch. There are 5 nodes. One is just the admin node. There are 2 GPUs here, but just one is a Tesla one. They are both Fermi series, but one is a GTX and one is the Fermi C2050. Everything is here. So this is roughly the test configuration, and I would emphasize this system is not used for anything except for just doing. So the code I showed earlier for CUDA or MPI, CUDA together with MPI, the Ohio State bandwidth test. These are the results using 2 nodes on the system. So on the lower side, you have size in bytes. and message size, and on y-axis you have bandwidth, and of course, as we know, higher is better. So here Jeff tested two variants of MVAPIT 2, 1.6 and 1.5. In the first case, the blue one is GPUDirect enabled, and you see the activity more or less is starting here. And then you see GPUDirect enabled with 1.5. I asked Jeff what is this dip for, and we don't know why this dips here slightly. Maybe some kind of buffering issue. The interesting thing is, after we tried the newer version with this 1.6, which was like fairly recent, about a couple of weeks ago, the GPUDirect enabled, which is this one, which is the blue one here, it really didn't change except this dip was improved. But the interesting was GPUDirect disabled, it improved quite a bit, especially after the messaging of 8 kilobytes. And so maybe your group can explain it better than I can. Yeah, okay, even for the specific to GPUs or just in general? Okay. So that was kind of a surprise. So do you think it would match to the top bit at some point? So then this will okay. So then we don't need GPUDirect. Yes? Yes? No, no. If we just run bandwidth test without any, yeah, because if you look at this thing, you say if def pinned else, so it just goes to the else part and nothing happens related to GPUs. So I would imagine, we haven't checked, but okay, I can then ask you, if we are not running just the bandwidth test without any GPU activity, do you think the red line will look like that or different? No, but this is GPU. Okay, yeah. Yes, so it will look different. I mean, we can run and check and maybe tell you tomorrow what happens. Yeah, because I don't imagine why, if you are not really using pinned region, and we are not doing GPU anyway, so that the bandwidth line should remain the same. Yeah, we can. I think we can definitely check, because then nothing goes on, because we are not running any GPU as part of the test. This is the same result, same numbers, but these are in terms of latency, and as we know, the higher latency is the bad thing. So we can. So that was kind of rather interesting when we tried the same experiment and we had the OpenCL version. The results were exactly identical. In fact, the counter changes, the counters of 3-4 counters, they change when you have a GPU activity going on. They had identical values. So that's why I feel like I think the runtime for CUDA and runtime for OpenCL is probably quite similar, because these were really identical. And if you know or you care to know about some OpenCL, there are more qualifiers in terms of how you reference memory. Like you can define read and write, read and write. I think this is default. And we experimented with some of these values, and really we didn't see any difference. So it may be that the driver, nothing has been implemented and it should change. And we we sent an email asking a description, but we didn't get any answer that whether it should or shouldn't change depending on how memory is referenced. So if you are concerned about writing GPU applications, but say, okay, I really must need to write in CUDA, now you can use CUDA runtime, and you can use definitely OpenCL. So after understanding how things work, how they should work, where are the soft spots or the points where thresholds are, then we went in and say, okay, because in online you find a lot of sort of claims and that you should see a lot of benefit on applications. So, and you can easily find these papers there where under certain configuration you do see some good performance benefit. So in this case, my colleague Jeff, he experimented with this MPI-benchmark, NAMD, and Ember 11. There is a lot of communication, and these codes have been sort of accelerated using GPUs for a while. But kind of a bit surprisingly, we didn't see more than like single-digit performance differences on any of these test cases. And there are several. There is no one reason, and there could be one or more of these reasons. The first thing is and I think this point was identified a little bit earlier as well, the way applications have been accelerated up until now is looking at GPU as an accelerator. So essentially, at design time, a code developer or an algorithm designer makes a conscious effort that I'm going to compute something, and if that compute is qualified or selected to be accelerated by GPU, I will send some data explicitly to the GPU. I'll accelerate that part. I will receive data. I will then send, if that data needs being sent to the network for MPI, I would do, and I would receive, and I would then start the whole process. It's oversimplification, but the idea you see here, there is no overlapping going on between the activities on the GPU and the communication, where you really can benefit by reducing these extra copying. So the codes we targeted, except for the benchmark version, the micro-benchmark, they exhibit something similar to this. So if your code has been done in this lockstep manner, of course, it would be very difficult to see if indeed your communication is accelerated and your impact on GPU part is there. So, and the other thing, if you can remember from the graphs I showed you for bandwidth, that you see the activity for very limited bandwidth ranges. So you can change that threshold, and I'll talk about it later. So in some sense, you need to know what are the message sizes or MPI message profile of your application. And then you have to call system setup, and together with Mellanox help, we sort of experimented and tweaked a lot of InfiniBand environment variables, some of them web-page variables. So at certain point in time, if your system exists in a certain status, you may not see anything. So it's rather sensitive, very delicate setup. And it could also happen that the configurations that were used and that were presented in some of those publications, we may not be using the same setup and same configuration. So since there is this dependence on so many different elements, and as if you recall earlier on, I showed you how to set this thing up, it's very difficult in some cases to observe huge benefit for applications. So what do you do about it? Like, right, throw a pen and say, okay, it's useless? No, you can do a bit of it. First, just make sure you are using pin memory. You can also make sure you are using the right MPI configuration. You can even send a note to Mellanox, or I mean, in case QLogic and web-page team, and ask them, okay, how do you set it up? There are publications out there that tell you how to do it. And we, of course, made those mistakes and we learned from them. The other thing is, what you can do is, if you really do know what is the size of your, what are the sizes of messages your application is communicating, you may consider changing those thresholds. But just be careful. Some of these things may give you some benefit in case of GPUDirect activity, but they may have an adverse effect on other things. And as I said earlier, this is just as things are now in today, and the performance benefit there is very limited. But going forward, things can be improved in many different ways. The underlying assumption here for me is that we will use GPUs for code acceleration or some kind of accelerated devices here. So what can you do? There has been a lot of noise last week or so, or I think a week before that, about CUDA 4.0 GPUDirect 2. And as we know, this is right now just between two GPU devices. Can we exploit it for another PCI devices? That has yet to be identified. I think most important for me, and this is the work we are doing, is we need to rewrite some micro benchmarks to show application people how they can, in some cases, overlay computation and communication to exploit the existing features of GPUDirect. And how do we do in applications is, because if the benefit is 30% and it's in very limited case, it's very difficult to make a case for applications to be changed in a significant way. So it would be rather difficult to convince application developers to take advantage of these things. So if I look at this picture, essentially what we really need is somehow avoid copying at all to the host memory, because we know in any case the PCIe chipset here is probably the weakest link in this current picture. So just to summarize, it's a very first step. It's an important step because at this point in time we are thinking of, okay, GPUs could be here, could be useful for HPC. And there is a lot of work going on there for all sorts of reasons, and we need to rethink the way we are using the main compute element and doing communication, involving them in communication. And then we can ask ourselves, okay, is this underlying assumption that we always going to need a CPU, I mean, to access other system resources? And if you say yes, we can do this incremental, like GPUDirect 1 or changes, and we'll see how far we go. And if we say no, and you probably saw several other announcements, what a lot needs to be done, and it can't be done in a matter of probably a couple of years. And from our side, the kind of work we do, because we are not hardware vendor, we are not really doing any low-level system software development, I think whatever is being thrown at us, like something like GPUDirect, we need to make sure, in our case through micro-benchmarking and some of the system-related efforts, that how we guide application developers that these new features can be exploited in these heterogeneous system cluster environments. And like I said, in addition to us, we have had a lot of conversation with Mellanox and from NVIDIA and from, of course, Ohio State to get this thing done. So, I'm done.
Any questions? No? Okay. Thank you very much.